Hi, my name is Michael Ainsworth,
And I'm Xian Li.
and today we're going to explain our final project, which is titled Selective Speaker Filtering.
Yeah, so our general purpose of the project is basically to have an input, and we'll be filtering all them by low pass, band pass, and high pass, and then amplifying their outputs with different amplifiers into speakers, which will then basically show some sounds according to the amplification and the filtering.
Exactly. So the idea is based on our input for each of the speakers, or our input frequency. Each speaker is going to work for a different frequency range. By running a network sweep, we're going to see how each one works at its different significant time period. So we're now going to look at our subcircuits. We're going to start on this side, and you can see we have our low pass filter right here. This is an active low pass filter. As you can see, it uses an op amp. And based on our resistor values, we calculated the gain of the op amps to be approximately 3.5 and the 3 dB cutoff to be approximately 7 kilohertz. The reason we chose our 3 dB cutoff to be about 7 kilohertz is because the human ear can hear up to about 20 kilohertz, so we want it to cut off before the human can stop hearing it. We're now going to go to the bottom here where we see our active high pass filter. Now, same thing, we use 2 resistors and a capacitor, and this one is designed to have a theoretical gain of about 10 decibels, or that would be our theoretical gain would be about 6.5 decibels. Our theoretical drop-off would be about 163 hertz. Once again, this drop-off is designed to be within the human ear range. The human can hear sounds up to about 20 hertz. So 160 hertz should be able to attenuate sounds that humans can't hear, or can actually hear, and won't be able to hear when it's attenuated. And in the middle, we've combined the two into a bandpass filter. This is an active bandpass filter using the same resistor values. The 3 dB drop-offs for the bandpass filter will be the same as the high pass and the low pass, and the gain will be approximately 10 decibels. This way, this will have a selective range of frequencies where the signal will be allowed through, and the other range of frequencies will be attenuated and won't be able to be heard through the speaker. We're now going to look at the next 3 amplifier circuits.
Yeah, so for the first one is a half-wave rectifier. Yeah. And so we use the, basically we went from the N side of the diode instead of going to the P side, which we have a different gain. For the gain for the half-wave rectifier was about 4. And so our second amplifier is our non-inverting amplifier, and this one had about a this one was more simple. It was just using a single op amp. The other one used a op amp and a diode, and so this one had about a 2 gain. The resistors were the same, and for the non-inverting amplifier it was 1 plus the ratio of the resistors, so it was about 2. And for the transistor amplifier, it was a little bit more tricky. We used a BJT and a couple capacitors to amplify the input. And so basically the gain of this was to be around 2 as well. So basically all of them should be amplifying it to a certain degree.
Yeah, this should make it a little bit easier to hear the signal when we actually run a sweep. So now we're going to demonstrate our project. First, we're going to have all 3 speakers attached, and as we run a network sweep, you should hear the top speaker for the low frequencies, the middle speaker, and the other 2 speakers for middle frequencies, and then the bottom speaker for high frequencies. That's basically just the way that the filters operate. So we're now going to run a test run, and you should be able to hear the sound throughout the time. Okay. We're going to pause that now. So now we're going to show you, it might be a little bit hard to hear through the phone, so we're going to show you each speaker individually and demonstrate how each one works for its specific frequency range.
This was low pass.
First, we're going to do the low pass. The low pass should work at low frequencies. You'll hear a very deep noise. And then, based on our gain, once we get to about 7 kilohertz, you're going to stop hearing it because it'll be attenuated so much. We're starting that now. As you can see, our network sweep starts at low frequencies, and you can hear the speaker right now.
Yeah, we're going from 10 hertz to 100 kilohertz.
Yep. Perfect. So as expected, once we reached high frequencies, around 7 kilohertz, it was unhearable anymore. We're now going to do our bandpass, which should have both components. You won't be able to hear it at low frequencies, and you also won't be able to hear it at high frequencies. This one's right here. It's running now, and you cannot hear it. Good. And then the last one we're going to run is the high pass filter. This one should not work at low frequencies and will only work at high frequencies. We're starting it now. So you can see you cannot hear it yet, but once we reach the 3 dB cutoff point, you should be able to hear it. Perfect. And you can hear how once we got to those high frequencies, we were finally able to hear the sound. So now we're going to show you our graphs that support what we've been talking about so far, and basically just reaffirm that our filters and our different amplifiers have been working properly. We will start with the low pass graph.
Right. So this is our low pass graph. You can see that at lower frequencies, the gain basically stays constant, and then as we start to get to the higher frequencies around maybe 7 kilohertz, it starts to drop off, and basically that means the volume will be getting lower and lower.
We're now going to look at our high pass filter.
And so for the high pass, it's basically the direct opposite. We have for the higher frequencies, it stays constant, but at around 100 hertz, 160 hertz
Yep.
around is where it starts to drop off here, and so the volume at lower frequencies will be lower.
We're now going to look at the bandpass.
And you can see that for the bandpass, it's basically the low pass and the high pass added together. The high pass makes it so that you can't hear lower frequencies, and the low pass the low pass makes it so that you can't hear the high frequencies, and the high pass makes it so that you can't hear the low frequencies. So it's basically
Yep. We'll now look at the amplification methods we used. This is for the half-wave rectifier.
Right. So this is for the half-wave rectifier. We can see that the input is a yellow wave and the output is the blue wave, and we can see that it's bigger. It's like it's more amplified. This is about 4 times the amplification right there.
Yep, that's our gain of 4. This is our non-inverting amplifier.
And you can see that for the non-inverting amplifier, we can see that the output is it has twice the amplitude of the input.
Yep, and it's the same direction, which implies the non-inverting. And lastly, we have our transistor amplifier with the BJT.
Yeah, this is a little bit more complicated. Basically, we can see that the gain is around twice the input for the output, and we did have to adjust the offset a little bit to make it look the same as the LT Spice simulation, but is how you can see that the gain is around 2.
Yeah, it's approximately what we estimated. So this demonstrates how our filters and our amplifiers all work together to make each speaker work at a different range. And it worked out really well, and it successfully did what we accomplished to do. Great, thank you so much.